Hello, in this lab, we are going to work on one-way ANOVA, so through one example. So we learned the basic terms of design of experiment, and today we learn the way to analyze your data. So give you one example. In this example, we are interested in the compression strength of different type of boxes. So there are 3 types of boxes, 1, 2, 3, 4. And then we test how the compression strength for each box. So for type 1, we repeated 6 times. Okay, type 2, still 6 times. So this is called replication. So this experiment, there is one factor, the type of box. This factor has 4 levels, type 1, type 2, type 3, type 4. And our response variable is the compression strength. So we like to know, is there any difference among the 4 types of boxes on the average compression strength? So total, we will have the data points. That's how many trials you have. That's a 4 multiply 6, 24. Okay. So how many treatments here? It's 4 levels, just 4 treatments. So if we plot the data, we know we can plot the box plot for type 1, 2, 3, 4. So the graph shows since type 4, the strength is lower than other 3. So in order to analyze, we have better understanding, is it true there's at least one different from others with regard to the mean? Okay. So we also can plot like a scatter plot. So we know the type 1, 2, 3, 4. So how we are going to use ANOVA to answer this question? The ANOVA is a way to compare the variation, okay, the variation between groups, okay, versus the variation inside each group. If the variation, the variation between groups is much, much larger than the variation inside of the groups, that means they are significant different. So at least one average is different from others. If the 2 variation between group variation and the inside group variation is very close, so we cannot have that conclusion. Okay? So that's why this method called analysis of variance, ANOVA approach. So now we look at the data. So this is the data. We just transpose like this here. So now what we are going to do, we need this part we call sum squared between the treatments. Okay. So I like to have this average of each group and compare it with the overall average. So we use X bar here, indicate overall average, okay, equal to average of all of them. Okay. X bar, that's the average of each treatment. So here, the X bar for type 1. So we can drag. So we need to calculate this part. That means we like to know the average, okay, of each group, how far away from the overall average. Okay. So we use this x bar over this specific, so we use the dollar sign, so we can copy the formula, and then squared. Okay. So this term just added, we add this together, okay, and multiply this ji. This j means how many replications inside of each treatment. So we have 6 replications. So this sum squared treatment just equal to you sum all this together. So this is how the variation from the overall, okay, and then multiply 6. So this is the sum squared treatment. So this is the degree freedom of treatment. We know how many treatment, just the 4 levels, right? 4 types. So degree freedom for this treatment equal to 4 minus 1. Here is the mean squared treatment. That's the average, on average. So the sum, the sum squared treatment on average divided by this degree freedom. So we have this on average, this variation from the treatment. Okay. So next, we are interested in another variation. It's come from, we call arrow part, or we call, this is the between treatment. And here, the variation is inside each treatment. So for this one, inside of each treatment, that means each value only compare, like we try to find out the variation from its own mean. Okay, that's the inside, the variation. Okay. So for this, the very first one, we just, the first value compare with its own x bar. Okay. So here we fix this row, and then this value need to be squared. The purpose of squared is if it's negative, it's still, I have the positive value, so I can add all together. Otherwise, you have positive, negative will cancel out. So that's why we consider the variation, we add all this together, we always use the squared term instead of original, just the difference. So this means the squared deviation for the first value away from its own average. Okay? So this calculate the variation within the group. Inside the treatment group. So we can do the same thing for these 6 treatments. 6, okay. Not 3, sorry, 6 value. That's all type 1, just 1 treatment. And then since I already fixed the row, and then I can move, just to copy this formula. Okay, it's always a good idea to just pick one to check, is this formula correct? So this one is P. The last one is this value, type 4, the last value compare. So minus its own average, okay? And then square. So this is correct formula. So we calculate each value, how far away from its own mean, okay? so the variation within the group. And then we can add them together. So why this one? We can add all this together, but this one we need to multiply 6. Because this, we only compared 1, but it represents the information from the 6 different values. So that's why we multiply 6. Okay. So that means all this variation from all these 24 different values. So this one, since each value we calculate the variation, so we just add them together. Degree of freedom. So here, degree of freedom, so within this group, so that's degree of freedom is 6 minus 1. And then I have total 4 groups, like 4 treatments, multiply 4. So this is the degree of freedom of this error part. So mean squared error is the sum squared error divided by degree of freedom. So once we know that this is average, we can consider as average variation from the treatment. This is the average, the mean squared error average, the variation from this error part, the within group, the variation. Now a little summary on what we have done. So first, we calculate the treatment sum of squares. So that's the variation of the sample means around the sample grand mean. That's the, I use X bar. Okay. So we use the treatment sum of squares. And then we calculate the error part, sum of squares. The error part is individual value compared with its own mean, okay, the own treatment mean. So for this, add together, that's the overall variability among these data. So one part, the variation from treatment, another part, variation from the error part. So anything not from the treatment, we consider as the error part. So how we analyze this data, how we can make conclusion, okay, we build a, we call standard ANOVA table. Okay. So in the ANOVA table, the first part shows the source of variation. It could be from between treatments, the variation from treatment, or the variation from the error, that's the within treatments, the sum of the squared variation. So we calculate this SST and the sum squared error SSE. We also know these two add together. That's the sum squared total, the total variation. And we know the degree of freedom, we calculate mean squared, treatment mean squared error. So how we can do the test? So that's called F-test. Okay. So ANOVA, so the test, so what's the hypothesis? So we know we have non-hypothesis, alternative hypothesis for ANOVA. So they compare the variance among the mean of each group to the average variance within each group. This is called F-test. The non-hypothesis, we assume all the treatment means are equal, no difference. Alternative is not all these population means are equal, or at least one treatment mean is different from others. So how we can use the test, use the F value to indicate if this value, we know this is the ratio, okay? That's the mean squared treatment versus the mean squared error. So when H null is true, so F test tend to be near 1. So because the mean are the same. So these two, mean squared treatment and mean squared error, will be very close. Both estimate the population variance. If H0 is false, that means mean squared error still estimate the overall. You put all the data together, overall variance. But mean squared treatment, that's the overall variance plus there's the positive function of the difference between the means. So the F ratio will be greater than 1. So this F distribution looks like this. So it has a long right tail. We also can calculate the p-value from this F statistic. We know the z-test, t-test, now comes f-test. Let's test the ratio of the two variance. And the same thing, we can calculate the p-value. So now we come back to see what's the f-test for this example. So f value equal to the mean squared treatment over mean squared error. So that's a ratio. So it's 25. That's a pretty large number. So what's the p-value? So the p-value is the probability your f value is larger than this 25. See, f larger than this 25.09. Okay. So in Excel, it's already have the F distribution. So since it's larger than, we will convert as 1 minus the cumulative probability. So that's F distribution, X value, and it needs 2 degree freedom. The first one is degree from the treatment. Another one is the error part, degree freedom. And this is cumulative. So it's very, very small. It's close to 0. So that means there is at least one mean is different from others. So for these 4 types of boxes. So here the conclusion. Since the p-value is close to 0, this indicates at least one mean compression strength, mean strength, is different from other types of box. So this is how we call analysis of variance to answer this question. Okay, are they the same or are they different? So there's one different. That means the type of box is significant. So this factor is significant. So for this one, it's up to you to finish this part. Okay, what's the factor in this experiment? What's the level? And the response variable replication, how many treatment, how many trials. So remember, for the experiment, since all this data should come from simple random sample, so we have total 24 trials. When you conduct the experiment, you should randomly to conduct your experiments. The order should be totally randomized. For example, you first try, okay, type 2, okay, and then you try type 3, and then type 4, and then type 1. So this is a randomization will get rid of all the other possible noises from the operator, from the time of the day, since it's randomized. So we can hopefully to cancel out all these variation from other possible factors. Okay, so you need to finish this part and also complete this one. So in Minitab also can give us the ANOVA table. So what we are going to do in the Minitab, so we copy the data, paste it here, and we go to Stat, ANOVA. One way ANOVA, since we only have one factor, okay, that's the type of boxes. So in this case, response data in separate columns. So you click OK. It will generate the analysis of variance table, the standard ANOVA table for you. So for this one, we need to copy. Yeah, it's easier to copy as a picture and paste it back just underneath this one. Okay. So then if you're finished, you know how to use Minitab, and also you know how to manually generate this ANOVA table. So that's the completion of this lab.